and gentlemen, it is time to engage the HR side of my brain. Yes, that stands for ham radio. Just as sexy as OF, which is OnlyFans, but without all the nudity, right? This gentleman freely and openly admits he might have possibly made a little bit of a mistake here. This has got the, I don't know how Ameritron ever got talked into going and using these guys for transistors, especially this part number. These are the RFP PP100s. I mean, it makes sense. They might have come from RF parts. PP100 transistors had a failure, complete and total utter failure. Let me show you what I mean. Open up the El Bago parts here. He was kind enough to send his own transistors, number one, but number two, the RFP PP100s here has completely come apart. He tried to change his own pills, as we say pills in this other side of my brain, the ham community, the amplification switch transistors. He attempted to change himself, and well, there might have been a little bit of trace damage, and the soldering iron wasn't quite big enough, and yeah, a little rough. It's okay. Like I've said in many videos, we're not here to give any bit of a hard time. He tried one transistor and he says, nope, I'm done. Because I'm just going to send it to you, let you figure it out. I said, okay. So we're here. This is RO58. Yep. Working from homeboy Rob today. I asked him, well, do you want to upgrade this? No. Do you want to change this? No. Do you want to do this? No. Do you want to Nope. Okay. So we're going to go in here. We're going to disassemble most of this amp board. We're going to take transistors out, put new transistors in it. That's after we clean the transistor pockets and everything. Reassemble, test, certify, and send right back out the door. Easy peasy, right? I said, do you want me to upgrade your power plug? No. Okay. Now, the next video I'm going to do is of the exact same amplifier, but completely different outlook. Same problem, the RFP PP100s. It's the transistors that's in here. This thing was originally designed, let's not us all forget, for the Toshiba 2879. Okay. Now, if you're not into sinking a ton of money, like I could probably at the time of the filming of this, the value of the Toshiba has gone down dramatically due to the fact that we have a somewhat stable transistor, which is produced by HG Semi. It's a 2879 version 16D08. The 16D08 is probably one of the better designs that they've come up with. There's newer transistors in that same transistor package case that have come from the same manufacturer that do produce a little bit more power, but they require a complete rework of the inside of this amp if we were to stick them in here. But for the most part, it's a one-to-one copy over. We might have to adjust a capacitor or two on the input and the output of this, but I would say most likely not. But we'll see. So the first step is we're going to rip the board apart. We're going to get the old transistors out, and then we're going to come back and we're going to see what we got to do for repair work. I know this one right here, we've got a little bit of a rip trace, but it's not a big deal. And the rest of the tabs of the transistor, well, they failed to come up. So let's get in here with an appropriate watt iron. And this board design's a little bit shitty because it is through board. So when we go to lift up some of these components, we got to be very careful we don't overheat and solder doesn't flow through and drip out, cause us to have a short. So let's get the transistors out and we'll go from there. Okay, so step number one is you're going to need some solder wick. You're going to need a fairly decent sized shovel soldering iron like this, which I've got set at 600 degrees. And then for the primary legs of the transistor, I'm going to use a Weller, so 100 watt. Same soldering iron. So this is the 100 watt soldering iron, just specifically designed for stained glass windows. It's got the little cushion handle on it. Okay, so what we've done so far is we just simply lifted these 4 legs up. They are tied. One goes here, right here, and the other one goes right here. Okay, these were just very easily soldered down to the legs of these resistors. This one here, I had to lift this out. I went ahead and I took the solder wick and pulled the solder from through this pass-through via here. And I did the same thing over here and clean this up. So this is where we're going to probably end up having our trace damage. So this diode is pretty important. This is part of the biasing circuit for both boards, both portions of this one pallet. So you have a 2-pill amplifier and another 2-pill amplifier. All right. So this will actually lay down inside thermal compound that sits on top of the transistor, and how this works is as the transistor heats up, the thermal compound conducts heat to the diode, allowing the diode to be a little bit more linear in its action with temperature in relation with the bias circuit. As the temperature of the diode changes, its ability to interact with the circuit changes up and down with the temperature. So now what we're going to do is I'm going to go in, I'm going to probably lift this side of the resistor out for part of the harmonic suppression of the flyback circuit. We're going to lift this out, and we'll go ahead and we'll lift this side out and solder wick out both of these pass-through vias, because when we put this back together, we want to take the component and slide it back in the hole and be able to solder it in place and not worry about us having a drip through short. It's where we overload a solder connection, it passes through in shorts. We also have to keep in mind underneath each one of the legs of the transistor is a giant opening, orifice. See that hole in the board right there? So we want to solder with the most minimal amount of shmoo that we can apply. So we're going to lift these 4 resistors out, and then we're going to come along and we're going to remove the ground side of this diode, which is in between each one of the transistors, and we're going to fold it back this direction. Once we have achieved that, that'll allow us access to all the transistors. Of course, obviously the first step would be removing the 4 screws from each one of the sides of the pallet, so a total of 8 screws, 2 per device. And like I was saying, you know, the transistor Toshiba market has gone way down in value. Like I was saying, at the time of filming of this video, we could probably go in and replace each one of these transistors with a matched pair of used Toshibas for around $75 a piece, and probably be able to put brand new Toshibas in there for around $100, $150 a piece, which is still astronomically high, taking into account I personally can remember when they were $10 a piece. But they're not being made anymore, and that's the laws of supply and demand. So, okay, kind of shooting this as a how-to, so maybe somebody out there, one of you guys in YouTube land, can take this and learn how to do this yourself. It just takes a soldering iron, a little bit of time, work slow, and using the right wattage iron. Now I'm going to give you this one little tip. You guys have seen me use this before on video. The tools that we're going to use to lift the transistors out, let's cover those real quick. I have my trusty, dusty $2 Amazon supplied dental pick. And when I mean $2, it came in a whole kit, I think, for like $3, or $2 for like 4 pieces. This dental pick. And then I have these directly from Best American Can Make hemostats that I've taken an old used transistor. I got out the MAP gas torch and very carefully heated these so that they go specifically into the openings of the transistors. Now I flared the tips. The tips of these are flared just a hair. The tips of these are flared out just a hair. So when I go and I grab onto the transistor, I'm not grabbing into the heat sink mounting holes below it. I'm literally grabbing just the transistor body. And I bent it in such a fashion that this groove This landing groove is precisely the depth that we need to have to be able to grab onto the holes of the transistor, so we have a little bit of torquing action, okay, if we need it, but it's not going to damage the ceramic lid cap on the transistor. I'll show you how to use these in just a second. So I just got done taking all the thermal compound off, and I wanted to point out that what we're using here is 91% isopropic alcohol. The reason we use 91% is if I could get 98% something that had been chemically dried, I'd use it as well, preferably over this. But for you guys, the home gamers, the 91% is about the highest isopropic content alcohol you can get. We don't want to expose the circuit to water unless we have to. 91% is the highest version of alcohol we can get through natural distillation. That's just evaporation and separation of chemicals without going to a chemical drying process. To get that extra 9% is really freaking hard. Alcohol has a tendency to want to absorb and carry bond with and remove water. So we capitalize on that as a cleaning agent so that it can, as it evaporates, it takes the moisture with it. But it works as a really good solvent for breaking down the thermal compound, which is on top of these two transistors here, this one here and this one here. So just take a little bit, just like regular rubbing alcohol, put it on a piece of paper towel and go in here and clean all the thermal compound off. We want to take that thermal compound off before we take a soldering iron into this area so that the thermal compound does not get into any of the connections. We'll try and keep the connection as clean as we can from any unwanted shmoo, I guess would be the best way to put it. So I think for demonstration purposes, we're going to pick on this transistor here first, and we're going to utilize our dental pick. You don't need this tool that I've created, and I didn't create it, I just made this. I can't take credit for this idea. This actually came from a friend of mine. His name is Zane Johnston. He owns Big Rig Radio in Phoenix, Arizona. And he came up with this idea because he does a lot of hot air soldering, and he builds all these specialty tools so you can reach down and, we'll say this is a little tiny IC chip that's right here. You just click, grabs on the edge of the IC, gets the hot air iron out, pulls the part off, ding, ding. Okay, so he's built himself all these little tools. Using that same mindset, he was harvesting, I guess that's the PC correct term. He was removing Toshibas from a bunch of old Kenwood radios, and he was using the dental pick method. Well, he came up with this method. You click this tool in place, and then you take your hot air iron and heat up the transistor, and you can just lift the whole transistor out of the pocket all at once. I don't like doing that because it has a tendency to float a whole bunch of other parts all the way around the transistor before the transistor comes up. But I guess if you're good enough and you got masking skills where you can mask the airflow up. Me personally, I like to use this as a control point, right? So I'll start my process, just slip the dental pick underneath the leg of the transistor so you can kind of come in here at an angle, and we can just very lightly, not with He-Man skills, we're talking like just that much torsion. The same thing here and the same thing here. We can heat the leg, lift the leg, heat the leg, lift the leg, heat the leg, lift the leg. And the idea with the 100-watt soldering iron is that we can get the entire trace surface, which is fairly large. It's a little bit, under 1/4 of an inch. Get the both sides of the transistor leg to heat up enough to where the solder becomes fluid, and we're minimizing the time that we have to soak the part with heat. That's the killer of the HFE gain in these transistors, is to sit there forever with an undersized soldering iron. And we want our solder to be smooth and not over temped. This amplifier in particular has these copper boards that are right here. As you can see coming off the transformer, we have this copper slab that hangs over the transistor, and it's to help carry more of the positive current to the component. As we can clearly see, we have a common ground reference through the heatsink through this screw, and also a common ground reference through the heatsink through this screw. Through trace supplementation, we're able to carry enough current to the center of the transistor. Inside, there's a little piece of material, a little tiny bar that goes across the inside of the transistor and takes this tab and brings them together. So the idea is that we can get more current through this one tiny little trace, because this is where our 12 volt current comes from. Positive side comes from here. So it's the actual electron flow path is from here to here, but I digress. Needless to say, this is going to be the last thing that we heat, and we want to be able to have the ability to slide the transistor out. Hence the reason why we actually need a really heavy duty soldering iron to pull this job off. So 100 watt iron. You can use the flat shovel tip on a Heiko iron and turn it up to almost its max temperature, and you'll be able to achieve the same result. So basically dental pick and a little bit of time. This tool is going to come in handy and grab on the transistor. Then we can heat this piece of copper up with the big iron. So we'll slide this cap out of the way. We'll slide this resistor, we'll just kind of fold these parts over a little bit. We'll heat this piece of copper up. The heat will conduct itself through the copper and it'll loosen our solder trace here. And we'll be able to lift by torquing back and then pushing this direction, be able to slide the component out, right? Now, if you didn't have this tool, what we would do is you're going to heat this solder. That's after you've removed this leg, and this leg. You're going to come in here with your dental pick, heat it, and with just the smallest amount of thumb pressure, you'll be able to fold this up and slide it out. And when we go to install this back in, there's two ways to do it. We can evacuate all the solder from here with a solder sucker and solder wick and overheat this entire trace a whole bunch of times and make it so we can slide the part back underneath it. Or we simply take the tip of the part and we bend it in the contour shape of the copper and we solder it to the trace and to the copper strip going vertically in this direction, going up. So we'd bend the tab here, fold it up, so we can just apply the solder on both sides and solder it into place. So, all right, let's do the work. Okay, so if you guys noticed, we struggled a little bit with getting this tab of the transistor to release. And how we dealt with that is we, instead of just leaving the soldering iron on there to cook, which is just heat is wicking all over the place at that point. It's migrating up here and it's going to affect our solder joints on the front of our transformer. It's going to affect all of our solder joints on these two capacitors. It's affecting everything. Simply pulled the iron away and went and got some more solder. So what happens is as the amplifier is running through its little heat cycle regime of running, it goes up and it goes down in temperature. Well, each time that happens, the solder gets a little bit more work hardened. The flux that's in the solder gets cooked out. Okay. So the solder's melting point changes with the lack of flux that's in it. So the term that we use to describe that is work hardened. So instead of super soaking the entire circuit with just holding the iron, holding the iron, holding the iron, we pull the iron back out, we wet the soldering iron a little bit with the solder, we reinsert the iron, and then we take and add a little, just the smallest amount. You've seen it was like a little worth of solder in there, and it flows down. It allows for more surface contact between the iron and the trace area, the work area, and then the solder flows into all the existing solder and allows that solder to become softer, lowering its melting temperature. So we get a better heat transfer, slightly lowers the melting point of the solder, and then we're able to slide the part out. So that's what these two transistors look like once they've been removed. So look at the legs and the ears. It's just the smallest amount of pressure you need to add with the dental pick. The idea is to come underneath the edge of the leg and then pull the dental pick out. So you're just trying to separate. We'll say this is the trace, right? And here's the transistor. The dental pick is going to come underneath the leg of the transistor, and we're wanting to just separate the joint. We don't want to go digging like we're on an archaeology experiment where we're trying to shove the soldering or the dental pick underneath the trace. We're wanting to just slightly lift up and bend the leg up till we increase the point where there's no contact between the board and the leg anymore. That's it. We're not trying to use this as a pry tool. It's the wrong way to do things. We just want to lift it a little bit. We shouldn't have to put any more energy into it than, like I was saying, about that much pressure. Okay, let's lift this transistor out, and then we're going to come over here and we're going to clean up this gobbledygook, which is really, honestly, don't mishear me what I'm saying here. This whole side is not that bad. Let's zoom in here and let's take a quick look at it. It looks a little rough, but it is really not that bad at all. So here's the side I did, and you'll see where I came back and I solder wicked here, solder wicked here, solder wicked here, and then over here, also solder wicked here. A little shiny bit, yeah, a little tiny piece of flux. I'm going to tell you how to take care of this and show you how to take care of this, all of this. We also take this opportunity to inspect each one of the through holes for the screws to make sure that we have no burrs here. Here, and here, and here, and here. Whoever Meritron contracted with to have this heatsink put together, they did counter bore the opening orifices of each one of the mount points, so we didn't have a burr. Sometimes there might be a burr, and that little burr that sticks up here right at the edge of the hole for the threads could be and has been the culprit of many transistors finding their way to the graveyard, because that little bit of inconsistency of smoothness will cause a transistor not to sit flat. You see this little solder snub that's right here? One, we're not worried about it right now, because when, yep, see, it just fell right out. Just fell right out. Once you see what we're gonna do, the next steps, you're like, okay, we're not gonna worry too much about that. So we'll lift this one out, but this is not that bad. There is a little bit of the trace right here that I have to repair, right behind this resistor where the trace got ripped, that I'll repair. And that's simply because I'm a repair shop. If I was the home gamer, when you lay the tab of the transistor down, you'll probably find that it matches pretty close to this, and you can just bridge this with solder for the most part. But I'll come through and I'll repair this. I'll take a little piece of copper tape and we'll fix this right up. I just got to fish. This is the bar that goes between the two tabs, by the way. That's what we're looking at. Let me bend this down so it makes sense to you guys. This is one tab of the transistor right here. This is the bar that goes through the transistor, and then this is the actual tab that makes contact on the other side. So we can see how the transistors internally they tie the two tabs together. But we also have the stock piece of transistor trace here. That's the leg of the transistor that got broke off. So we got to come in and clean this out, just kind of de-infect the field. It's not a big deal. Not a big deal. Okay, so let's go in here and let's repair this portion of the trace real quick. So we're going to use our 91% rubbing alcohol. We're going to put it on a Q-tip. We're going to come in here, and the main thing that we're doing is removing the surface flux from the trace and the PVC, or PC, the phenolic, the copper-clad, silver-plated phenolic that's here. We're going to just go in, we're going to clean this area up. We just want to get all the residue off of here as much as we can, and from the surrounding area. Just get this cleaned up. If the phenolic becomes burned, carbon scored, or the field becomes polluted with any kind of other thing other than just our copper here that's got our solder on it, we have to clean all that away too. It's not uncommon in the field that I work in most of the time where this gets burned. The actual substrate gets burned up. We have to clean all that burn out of there. That carbon is conductive. So then we would go back and I would take and put a little piece of Teflon like this. This is Teflon roll. Sneak a piece of Teflon underneath the backside, and then I come back with a 2-part injectable epoxy which is, what's the name of stuff? 5,000 PSI, IPS 5,000. Then I backfill that board with the epoxy, and then we'll put the trace repair over the top of that. And so this is now clean for the most part. We want to give it a couple seconds for it to dry. Good minute or two. I just took my finger and run my finger in here pointing at things. So the idea is to clean until the Q-tip comes up. Clean. Okay. So now we'll let this dry for a few minutes. Just let this get totally cool and ready to rock and roll. And let me reach up above me here and get the copper tape. So this is copper tape. You can literally buy this off Amazon, eBay, Mauser, DigiKey. Everybody and their brother sells this copper tape. It comes in about 15 different thicknesses. I cannot remember the mil thickness of this, but the idea is that we're going to create a new trace that will probably come back to, let me zoom you guys back in. It'll come back to about here and then go forward, right? So we'll match this edge of the trace, and then we'll take our razor knife and we'll cut this edge of the trace, and then we'll cut the front edge of the trace. But we're just gonna lay it right over the top. And when we go to solder it, the solder is gonna wick out, and it'll have all that surface area, and then we'll have a nice flat area for us to bond the leg of the transistor to. But if I wasn't explaining this to you guys on video, it would have been done already. So let me get some tape pulled. You lay it down with an X-Acto knife, you cut it out with an X-Acto knife. You'll see how this looks. I'll bring you back once I get the trace in here and laid down the way I want it. That's it, that's all she wrote. Just the smallest amount of copper tape. We're gonna come in here with our Kester 959T. I love this stuff. Just come in here with just a littlest of dab of flux. Not a lot. We're not wanting to go completely stupid here. And let's see if I can take my small soldering iron reach around the camera, reach around on the other side of the camera, and we just come in and we flow from that edge to this edge and across. Just flow, we flow, just like that. Trace repaired. Super simple. And you can do the exact same thing. I've done it all the way down to very, 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 like the size of freaking sewing needle thread, the same way. And you can get the copper tape cut in multiple different widths, but that trace is now repaired. And thank God we're on the input side, so there's not a lot of voltage, current, or RF present. But even if it was on the output side, I'd feel perfectly comfortable repairing in such a way that once the transistor's in, that's a little piece of flux, by the way. Once the transistor is in, I don't see us having any kind of problem. So the next step is we need to clean this entire thing to make it ready for us to install the new transistors. So the primary goal here is to work the solder flux, or not solder flux, the thermal compound out from the pill pockets, transistor pockets. So how we start doing that is simple. This fancy device called a Q-tip, and we get in here and we just simply pull it all up with the Q-tip. And our only goal here is to get the large chunks, like earwax. Want to get this down to the anodization coating, or anodization. That's not the anodized coating. We want to get all the big chunks up. So that's one. What you guys didn't see was me preparing for this next step that comes after this portion that I'm showing you now. I have here this towel, my absorbent towel. I took my pair of scissors and just slid it underneath the amplifier to give it a slight from level, just kicked it up just a little bit, because we want the alcohol that we're going to induce into this environment to simply run out of the gap down here, run down the heat sink fins, and come onto this towel. That's it. So like I said, we're just after the big chunks, and also this allows us to get the big chunks of solder that might have flipped out of our solder space down into the pill pockets. Allows us to retrieve those before we go and we flush the area with rubbing alcohol to clean it. The idea is to try and keep the amount of solder flick that could possibly be underneath the board to a minimum. That way we don't have to lift this entire board up. If you do get solder flick underneath the board and you cannot blow it out with an air compressor, or taking a piece of paper and pushing it underneath the board to clear the short or to clear the solder ball, relax. It's just a little bit more effort. You're going to undo the screws, lift the whole board up, and just wipe it clean. So you'd undo these screws here, and this one back here. The whole thing will come up. You just reach in there with a towel and wipe it clean. But we don't need to do that today. So now we take our trusty, dusty, this is, I believe, an Ace paintbrush, yeah. Ace hardware paintbrush. Pour a little bit of rubbing alcohol into the work area. And now we're cleaning just the tray. We're not pushing hard enough to go through into the pill pockets. We're just moving the alcohol around to break up most of the big giant pieces of flux and to clean the trace area. Now we start pushing in. So we push into the pill pocket, push into the pill pocket, push into the pill pocket area. And what we're doing is we're moving this alcohol around, and it's breaking down the thermal paste that's at the bottom of the pill pocket. So we come back in with a little bit more rubbing alcohol. Clean our brush. Like Bob Ross for some reason. The OG Happy Trees. We all grew up watching Bob Ross. All of us. God bless PBS. WGBH botched them, man. They gave us Nova, Bob Ross. They gave us Julia Childs, the OG or Drunk on Television Broadcast Network. Yeah. There we go. Then we tilt this up. Give it a really thorough rinse. And we want all this to run out of the amplifier. We don't want it to get into any of this or any of this over here. We want to keep this to a minimum. Not the alcohol is going to conduct or cause us to have problems. We want to provide it the shortest path out. So we'll let this sit for a minute and we'll let it drip dry. Not going to take toilet paper and boop boop. We're going to let it drip dry. Okay, so now we've let our drip dry process work its way through. Take a little bit of rubbing alcohol and come across the bottom of this. And what we're doing is removing any other of the oil or schmutz or anything that leaked out of the vent that we were capitalizing as our drain. Come along and clean this up. Not that it affects the performance in any way, but when it goes back to the customer, we don't want to give it back to them with a bunch of grime on the bottom of the tin. Okay, so this is my thermal joint compound. I was looking at this date and the batch of 05-16-07. It's now 2024. I've used, with all the transistors, when I first got this, it was full up to about this line. So just guessing, I've used about that much since 2007. This is really silly cheap. I see people, they've gone down this rabbit hole. They're like, oh, there's all these advanced thermal compounds for computers. I'm going to put that technology to work and I'm going to break the sky open with a new invention. And I watched one guy in particular, a friend of mine, go down this rabbit hole specifically with LD-MOS transistors, and he used he likes to read things on the internet, and his brain focused in, he tunneled down on the ability of the compound to do its job, which is marry the two surfaces together. Down on a microscopic level, the anodized coating isn't perfectly flat, nor is the heat sink, nor is the foot of the transistor. So this is just, all this does is to help transfer the heat energy from the bottom of the transistor to the heat sink. If you use too much of this, it'll act as an insulator. Too little, and you're going to have what they call as a gap. Okay, you'll have an insulated gap. Also too much, what happens is because the transistors, these Chinese transistors, don't have a canted foot, and what I mean by canted is the Toshiba transistor, if you look at it from the side view like this, the front end of the foot actually, it's on a slope. So when you go and you thread the screw down, it pushes the center of the transistor down. This doesn't have that. So you have a problem that I call hydraulically cupping. It's because this is a grease, it is non-compressible. This is a non-compressible substrate, right? Which many people have done lots of tests on. My favorite one was by AVE, where he takes thermal compound and puts it two pieces of plexiglass and goes, pushes on it. Then he created a little bit of a pocket in it and pushes on it, and the plexiglass breaks, right? And we're talking thick, like acrylic, right? You have thermal cupping, and that's where the thermal paste, the hydraulic pressure that you're applying to it by tightening down the screws, the transistor, the material that makes up the transistor is so soft, it cannot impart enough force to smush the thermal paste out of the way underneath the component, and it'll cause the transistor, instead of sitting like flat, it'll cause it to cup in the middle, bend. And that won't, there's not now you've created a void. Guys will go down this rabbit hole with thermal compound and they way overthink the steering wheel. The worst thing in the world is to use anything that's got metal in it, especially in an RF environment. It might work for a little minute, but eventually that compound will break down from the heat exposure, the drastic heat exposure that we're putting on it, and it becomes a capacitive effect. They're like Arctic Fox, silver Arctic Fox. Don't ever use that stuff. It's horrible. It migrates around. It doesn't stay put. It'll migrate around, and in the PC world it works great. There's enough insulation factor there for it. In the RF world, there's not. The other thing is liquid metal. Liquid metal has a tendency to creep and crawl over time. The thermal characteristics of Arctic Fox and liquid metal compound are great. They're a great, between the heat sink and the transistor, it works awesome. Absolutely awesome. It takes up the little tiny micro spaces between the two parts that you're trying to smush together, and it works as a great heat transfer device. The problem is, and this is the logic I get thrown back in my face, and I just kind of chuckle. I'm like, you'll see, because nobody wants to believe me when I tell them, like, hey, I've already done all this. I've done this. I've seen it fail. Don't repeat my mistakes. Well, it works great in a PC world, so if it works great on that, $900 or $4,000 CPU and my cooler attachment for my CPU, it should work great for this. Wrong. Yes, its insulation voltages are great when it comes to low voltage stuff, 12, maybe 40 volts, DC. We're working with RF, which is an AC signal, and the voltage of the RF is much, much higher than the DC signal that your DC base carrier of the electrons that we're providing for the transistor work. The signal is amplifying is much higher in voltage, right? Well, in a computer, we're worried about low voltage. Okay, and so yeah, it's dielectric constant would be its fancy word. Its insulation value as a thermal compound works great in a computer. In this environment, it's horrible. So just don't even try. This thermal coat is really the best stuff. Been down this rabbit hole super deep. There's a gentleman on YouTube that is a professor, and he runs a really cool educational channel. And he went in with his group of undergrad students. They developed a fairly cheap thermal compound that you can literally make at home that works really well. These are, I HFE gained these, so I know that these need to be matched and these need to be matched. That you can make at home, or you can order from him, and according to him, the data doesn't lie. The thermal compound that he's developed does work a little bit better than this. The problem is there are no statistics when it comes to RF exposure, and I don't feel like possibly exposing my clientele to something that isn't UL certified, or at least ROS compliant, even though there's nothing in it that could cause cancer. Because I've looked at that, I've seen that, I'm well aware of that. Now what we just did is we put the smallest amount of thermal compound on this transistor, and I call it painting it like paper. Okay? So we have our silver foot of the transistor, and I want to put just enough thermal compound down that when I take the two transistors and push them together, so I'm pushing them together, just enough thermal compound down that there are no thin spots in it, and it's about the whiteness of paper. That's it. We don't need anything more than that. A very thin amount. If I was building the amplifier up from 0, I would take blue painter's tape and I'd mark off each one of these areas. I put thermal compound on my finger and I go, and then I'd come back and thin that compound down until it's less than the thickness of a piece of blues painter's tape. Very thin. A little bit goes a long ways. when I was a young man, before I understood anything about anything. Not saying that I don't know anything about anything now, because I don't know shit from Shinola. I'm here to tell you, when I was a young man, I would take the thermal compound and be like, and put them into the transistor pockets, and it did nothing but cause problems. I thought I was doing myself a good, because I thought more is always better. That's not necessarily the case. And after about my 5th or 6th friend that came back and said, hey man, the transistor popped, I had to go out and figure out why, and the only thing I could figure out is I'd put too much thermal compound in there. Transistor bowed, number one. Number two, there was just too much compound. It was acting as an insulator at that point. I want to circle back to one thing real fast before we go and put these transistors in the pill pockets. Put the transistors into the transistor pockets in the board. Before we commit, we take this and put this in here. What we are going to do, and what I suggest that you do, is you take a fresh, dry Q-tip. A very fresh, very dry, clean Q-tip. And we're going to go over each one of the pill pockets, dragging towards the center. And what we're looking for is on the transistor pockets where the screws pass through into the heatsink, we're looking for any little copper or cotton balls or burrs or hairs that come off the Q-tip. If we have none, it means we're good. And what we're inspecting for is, once again, any kind of metal lip that might be present around the thread holes in the heatsink. Each one of the 4 heatsink pockets. Now, what I did do is I let it drip dry. I blew this entire thing out with an air compressor, because once again, this is made by Mighty Fine Junk. And as we all know, our 5 and 8-year-old grandchildren, within 5 minutes of us teaching them how to solder, can solder better than most of the technicians that have been in MFJ forever. That's not just a running joke, that's a fact. I don't know where they get these people that solder at MFJ. I'm pretty sure it's China, but the solder work on most of MFJ's products is deplorable on a fine note. So, blew it out to make sure there was no other solder schmoo in here, because now we've moved the thing around, we put liquid to the situation, there might have been other solder balls in here. Went down here and spray all the way around it, down underneath all these boards to give us the best chance for success. Okay, let's go ahead, and we're going to lay our transistors into the hole here in a second. Each one of these transistors, there's 4 tabs. Let's get this in frame. Each one of our 4 transistors, each one of the 4 transistors, there's 4 tabs per transistor. You will notice that the one tab has got a cut in it. See that little nick in the corner here, the top corner, right there? We take this and we point that towards the big, big transformer. We want it to be faced that way, okay? That's the one where the positive electrons flow from and to. And that's the direction of the RF, that's the output side. So we want that cut tab. You'll also notice that I bent the tab up. And that's to compensate for this copper plate that's here. Okay? Let's go ahead and we'll slide these in the hole. The other thing is that we want to make sure that this area is completely clear. All of these areas that we're going to solder and work in are clear of thermal compound. I keep looking at my hands out of habit. And when I go to grab the transistors, I'm trying to grab it by the edge of the ears, not this. No pinchy. The reason for that is we want the oil and the grease and the slob that's in this thermal compound, and the oil and the grease and the shit that might be on my fingers, to not get smashed into this very slightly gold-plated tab. I want to try and keep those joints, those solder joints, as free from oil and grease as possible, right? Right. Okay, so now we're going to cover actually tightening these down. So we have all 4 of the transistors in place. We've already torqued these down, so we're going to cover this here real quick. Let me back this out just a little bit, because I want you to be able to see the handle of the driver, how I'm manipulating this. Most of you guys are not going to have the fancy driver like this. Let's just embrace the fact that maybe I've done more than one of these in my life, right? Or more than one amplifier that requires the same kind of Allen wrench. If you're using a set of Allen's keys, you literally don't want to tighten it any more than about 2 fingers. Do not use a drill. Do not use your Whack-A-Chack, Ryobi, Milt, Twatty, DeWilt Fricky tool to get in there and don't do that. Okay. I have the lowest powered Ryobi drill that I use when I'm putting in, let's say, 48 or 24 or even 16 transistors. My hands are getting old. I don't have to do this a whole lot anymore. My wrists are getting weak, right? I'm married, I'm just saying. To do all these by hand is a little stupid, but what I'll just start the screw, and then before it gets to the bottom of the pill hole, or the screw hole, I'll stop, and I come back and I tighten every single one of them by hand. The chance of either breaking the screw off are incredibly high, or 2, stripping the hole out. This is such a small thing that, I mean, I guess you could drill it and helicoil it and all that crap if you wanted to, or go to a bigger screw. Just avoid all that hassle. So I will tighten these with 2 fingers. According to the book, we're talking about, I think I read someplace it was like 14 or 15 inch-pounds of torque. We want it tight, but we don't want to, like, if you got an Allen wrench in there, we don't want to be like, we're just tight. Now what I like to do is I'll bring them down till they're a little bit snug like this, and then let it sit for 20, 30 seconds. Because remember, we've got all that thermal compound underneath there moving around, right? So I just come back, give it another quick little twist. Literally, no more pressure than what I can generate with my thumb and my pointer finger. Not a lot. Doesn't need to be a lot. See, I'm just getting a little bit more twist out of it. And that's from the thermal compound settling. All right, transistors are now technically in. So, what I like to do is, once again, we'll take our good friend, our Kester 959T liquid flux, and just give a little drop on each tab. And we do it at the edge of the tab, because let's face it, most of the current and electrons are flowing through the bottom of the tab. So we want the solder to flow down and under. Don't need much, like I said. A little drop will go a long ways. That's it. That's all it took, was like bloop, bloop. Okay. So now I'm going to move you guys over here so I can actually do the work, and I got to look like a hero on YouTube, or otherwise I won't be able to sleep at night. It's not true at all, but let's grab our 100-watt iron. Let's go over here and clean our tip real quick. And this is going to go really, really fast. Flow, flow, flow. Flow, 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 and we're done. Flow, flow, flow. Wait, wait, wait. Flow, 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 and we're done. Turn our solder blade this way, heat and flow. Solder blade this way, heat and flow it in. Solder blade this way, heat and flow it in. Solder blade this way, heat and flow it in. Solder blade this way, heat and flow that in. We're letting the solder flow down the tip of the iron onto the leg of the component and then letting the leg of the component transfer the solder over to the joint. If that makes any sense. But because we have the bigger, heavier iron, the solder flows very quickly. Meanwhile, the part's not being exposed to a large amount of heat thermal transfer. The same amount of energy is going into the solder joint. There's no doubt about that. But the quantity and the time of the exposure of heat, we've minimalized it just by using the right tool for the job. When I see transistors come or amplifiers come in here and the transistor solder joints don't look like glass like this, like what we've created here, the number one thing that causes that problem is the soldering iron tip too small and it's not able to transfer enough heat. That is the number one soldering issue, that and cleanliness and prep work, in that order. Too small iron, the work area isn't clean enough, and there wasn't enough prep work involved. So look at that. Turn the gain way down so we'll have no shiny surfaces. See how smooth the solder joints are and how they all flow together perfect? That's what we're looking for. Now, another tip that I can give you guys, if you choose to, like the pro guy, if he's got one that he's always got to run it 1,000,000 times its output and it keeps popping transistors no matter what you do, you can take the last little edge of the transistor and fold it up like what we did with the cut tab here on the top. That way you can get in there and grab a hold of it with a pair of needle nose and it'll help you peel it out a little bit easier. So you're not having to do the dental pick thing. And it's the same thing as the thermal compound. More is not necessarily better. We want everything to be as smooth as glass. There's no little solder balls or nothing. This is where I go and I'll take yet some more 91 proof or 91% rubbing alcohol. I'll re-clean this entire area and then I'm going to come back and blow it out with the air compressor yet again. Because every once in a while you have that one little solder ball that'll pop out as you're soldering. You don't catch it when you're doing the work and it could cause a whole problem. So we'll flush this whole area again and we'll blow it out with the air compressor. Okay. So basically all we did was put all the other parts back. We put the harmonic balancers back in place. I call them flybacks because it's the guy that taught me how they work, referred to them as. And we soldered everything else back in place. And technically we could run this. Small problem, we have some other burned up parts we have to think about. So everybody associates this burn, when the thing goes up, they associate the, oh, it smells horrible, it smelled like burnt plastic and blah, 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 save the whales. These two resistors, when whatever happens over here in the amp board, when that falls into imbalance, the differentiating output potential of the differential in the output potential between this amplifier section and this amplifier section, we put the two bits of signal back together here through this toroid. When the imbalance happens, it'll cause an uneven load on this combiner network and it'll cause these two resistors to burn up. As you can see, they're obviously discolored. It's very simple. These are 5 watt, 100 ohm carbon pack resistors. So we do not ever, and they look just like this, new, we do not ever want to use a wire wound resistor in this portion of the circuit because now that turns into an inductor. So metal film or carbon pack, if you can find a carbon pack. So let's just take just a minute. We're gonna take out these 4 screws. We'll lift the board up. We're gonna desolder these resistors. We're gonna put the new ones back in their place and we'll be off to the races and running. Okay, so power's hooked up. I got my foot pedal hooked up. Everything's hooked up. Amp is in. We'll flip it down into the off position real fast. Over here, this here is 1,000 watt in peak, 1,000 in average bird, whatever. 5-watt slug in reverse, run on 12 volts. We're going to use the bench ICOM 7300. Now, leave the mic gain 100%. We're going to leave the power output level at 100%. We're going to start down on 160. Let me show you the input power. Hello, 1, 2. Hello, 1, 2. So we're going to put 80, 90 watts worth of drive in it. Let's turn the amplifier on. Hello, 1, 2, 1, 2. There's our 500 watts peak. Let's go up here. Look at the ICOM. 1, 2, 1, 2, 1, 2. And what we're looking at is this bar, the SWR bar. Hello, 1, 2, 1, 2. SWR looks great. So now we'll jump up. We'll go here. We'll type here. We'll go here. Without changing a single thing. Hello, 1, 2, 1, 2. Oh. Man, I've really got to fix my foot pedal. Yeah, there we go. Hello, 1, 2, 1, 2, 1, 2, 1, 2. Looking at the SWR bar. Still our 100 watts worth of drive. Hello, 1, 2, 1, 2. We're going to see that rolling off performance. So now we'll go on up to the upper end of the band here. We'll go here. 1, 2, 1, 2, 1, 2, 1, 2. Once again. Hello, 1, 2, 1, 2. Now we already know for a fact that the amplifier is working, right? So now all we're demonstrating is that the rest of the systems on the amplifier check out. Change bands again on the front of the amp. Go to here. Hello, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2. 1.4, perfectly acceptable. Hello, 1, 2. If I don't check every single band of the amp operating, and then just by chance there's a problem in something else, and it might have been broken when it came here. As soon as I say, okay, it's tested, and I send it out of here, the guy on the other end, if he receives it back, he's like, oh, wait a minute, hey, this band's not working. And then I got to end up eating it. So we'll take a minute, and we'll go through all the different modes. So now we'll come up to the radio. Let's see, what did I just select? 14 through 21 megahertz. We'll do 21 megahertz. Millions of cycles per second. Megahertz. Once again. Hello, 1, 2, 1, 2. And remember, these tests are all done at 12 volt. Hello, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2. Good deal. Now we'll go to the aux position on the amplifier, which is the 10 meter portion. And since the 10 meter adapter board has been installed, I'll go right here. Hello, 1, 2, 1, 2, 1, 2, 1, 2. Let's go over here. Hello, 1, 2, 1, 2, 1, 2, 1, 2. So let's make sure we're in the aux. We are in the aux position. Let's go here, and just out of curiosity, let's take and we'll roll up to the upper end of things here. Hello, audio, 1, 2, 1, 2. Okay. And we'll roll down to the bottom end of things here. Hello, 1, 2, 1, 2, 1, 2. Okay, so this amp is set up a little bit better for the lower end of the band, but we are in top shape. Let me squish those coils together a little bit. Hello, 1, 2. That's better. What I did is I made the observation that this was spread out a little bit farther than I wanted. So now, instead of the 350 watts, hello, audio. Getting 375, almost 400. So now we'll go down here. We'll turn on the workbench power supply, which will bring the voltage up. And I think we're set at like 15 volts. So we'll see what we get for output. The radio is going to do a little bit more drive. Transistors can work a little bit easier. Hello, 1, 2, 1, 2. So we're seeing 500 watts. Let's go back down low where it's able to make power a little bit easier. Hello, hello, 1, 2. Oh, hey. Aha. To our overdrive position. I've covered this in many other YouTube videos when it comes to these. The overdrive is incredibly sensitive on these things. The way they have it set up is that if this amplifier produces more than 500 watts, it will go into overload protection. The amplifier circuit is totally capable of doing more, but they put this in here to help keep you safe. Now, the standard was different when it had the Toshiba transistors in it. The overdrive protection was set higher. So you will find with the Toshiba transistors in here and with the overdrive protection turned down a little bit, you can get a whole lot more power out of this little thing. But here, we'll start immediately into trip. Okay. We'll dial the power on the radio down to 80. Hello, into trip again. But we saw 600 watts. So we'll turn the power down on the radio to 70. Hello, 1, 2, 1, 2. 600 watts max. And that's just the protection circuit inside the amplifier that's making it work that way. Output. We're looking at these two resistors back here. Nothing's hot. We're looking at here. Input attenuator. Nothing's hot. Harmonic suppressors. Nothing hot. Bandpass. This relay, this is the one we're currently working on. It's the only thing that's warm. This all looks good. So the only thing to now double check is our amp gauge on the front of the amplifier. Hello, 1, 2. Hello, 1, 2. Oh, into trip mode again. Turn the radio on down to 60 here. Hello, 1, 2, 1, 2, 1, 2. Audio. Meritron. MFJ blows. Hello, swallows. Hello, 1, 2. This is a win for all the ships at sea. Well, hopefully somebody out there finds this useful. I'm going to tag this just as it is. Basically, how to go about changing your RFP PP100s. Ugh. Damn X-Force and his manipulation of the world and not thinking about how it might affect others and people all down the line. At the time when HG Semi was developing these transistors for the American market, the person that he was using was X-Force USA, and the gentleman that ran that company, which is now defunct and out of business, he did not want to go back and say to HG Semi that, whoa, all the power for the whole house shut off. Whoa. Well, we'll be back when the power comes back on. Power's back on. So like I was saying, he didn't want to go back to North or HG Semi and tell them that the transistors are having such a high failure rate. So he was going and telling everybody that was listening, oh, these Chinese transistors we were getting are fine. They're just fine. And instead, what caused the problem after that was the transistors, the PP100, which was his term, his label, based off of his test data, his test pool, he just desperately needed transistors to stick in a hole, because at the time there was no viable replacement for the Toshiba. So he was slamming these and everything he could get his hands on, the PP100s. Well, there's been a large group of us that have made a small fortune from us having to replace those components. because he didn't simply want to say to HG Semi that they were having a failure rate that was unacceptable. They had a tendency not to like high SWR aspect ratios, right? Well, most transistors don't. The Toshiba, I think, had a 65:1 SWR aspect ratio before it would fail. So it could handle almost a dead short intermittently before it would fail. The PP100s have something like a 5:1 aspect ratio. So they don't handle the high SWR issues with the circuit whatsoever. And they also had a heating failing issue that the insulation material between the first and the second layer of the transistor was failing, like a lot. So then when X-Force started to go defunct, we were able to get a hold of North and get him to understand that we were having a failure issue. He would come back, well, I've got largest importer, blah, 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 never reports back that I have a problem. Right. Well, there were some other motivations behind that. In the interim, what happened was companies like Ameritron and I think Yaesu actually bought a whole bunch of transistors from HG Semi based off of that data pool. And well, here we are today, replacing these PP100s with a later version of HG Semi or HG transistors, with a later version that's, well, got a higher insulation value to it and doesn't break down quite as easy. Yeah, one man's greed affected so many people, and nobody ever wants to talk about that. But it is what it is. Gentlemen, we're done. I'm going to throw the tin on this. This is ready to go home. I got to get this all wrapped up. This guy's already called and talked to me about wanting to get paid, wanting to pay me and get this thing back as quickly as possible. So, yeah. Literally, the power went off, phone rang, and it was him. But we're done. This thing is 100% good to go. And, yeah. I appreciate you all watching. Appreciate all the Patreon support. Thank you guys for coming and helping me out with the channel a little bit. Yeah. On that note, I'm out. Big thanks to everybody. I appreciate everybody's subscribing, the thumbs up. Make sure to hit that notification bell. If you're interested in wanting to help us, come down here and support us on patreon.com. Big thanks to Penta, Siglent, XS, MechMan, Bird, Coaxial Dynamics, all of you guys, and every single one of my Patreon supporters. I'll see you, gentlemen. Click, click.